Ok.
Perfetto. Allora, guarda.
Accetto. Io mi smaschero.
Io direi che puoi procedere.
Io posso procedere.
Perfetto. Students, a short introduction of Professor Alessandro Gargini. He is Professor of Geology at the University of Bologna. He is an expert of groundwater and interaction, water, land, and related processes. He will present something related to the influence of climate on geological hazards. So I think it is indeed something that is perfectly integrating what you have seen with me related to climate change and water risks, and what you saw with Professor Navarra and Professor Rossi. Alessandro, the floor is yours, please.
Thank you so much, Alberto. I hope that people in remote are listening to my voice. If there is some problem, please tell me. And obviously, I hope that you see the screen and the slide that I'm going to present. Okay. I don't know if anybody of you has some training experience in geology. I see your kids making no. I don't know, all in the remote people, there is somebody that is training geology. I know that you have already had some lesson by Veronica. Climate. I'm not talking about the past, I'm talking about the nowadays situation, the present days, and making and so also what we call as climate change and geological hazards. Hazards basically are related to water. In this the water distribution in the surface of the earth from two perspectives: too much water in one case, too few and scarcity of water in another way. So there are two faces of base of the coin, drought. So aridity and lack of water at the surface. I think it's also important not only geological hazards related to water, but geological hazards in general. So including earthquakes, including volcanic eruptions, including all the processes that determines an undesired effect, an impact against human beings and the society. Because all the geological hazards have in common basically the unpredictability or the very difficult find a solution to cohabit with them and so to cope with their effects. This is an introduction. I have prepared for the lesson of today and for the lesson of the next week a certain number of slides. I'm not sure to be able to present all these slides because it depends on the duration of the lesson. But by the way, I will try to do my better about that. These are the topics of the lessons. Basically, are there in these 6 hours completely 5 lessons of 5 different topics. The first one is a definition of what we mean about geological hazards and risk. And then we are going to observe the processes. It's important because you are not a geological training, a geological formation. And so we need to know which are the processes acting at the surface of the Earth, so what we call as geomorphological processes, and what are the processes below the ground, so basically groundwater flow. Then in the last two lessons, we are going to observe and to analyze which are the effects of climate change on the hydrogeological hazards and how can we react and coexist with these geological hazards, hydrogeological hazards, in terms of mitigation and adaptation. Geology is not only minerals. Many of you, perhaps in the high school, have made some lessons about earth sciences, and some of you perhaps is fond of minerals, but geology is not only minerals. Geology is not only rocks. Geology is not only fossils that are remnants of old life in the earth. Geology is not only volcanoes. Also, if, for example, if you have to, in the field of volcanology, you have to consider the volcanic risk. So the probability that some volcanic phenomena could have an impact against human beings and society. But also volcanoes is a typical geological phenomenon, obviously. Also earthquakes are a geological phenomenon. And also earthquakes have an impact against the society and the human beings in relation to the movement of the ground, acceleration of the ground, and seismic effects at the local scale, and also inducing landslides and tsunamis. I have some videos during this lesson. This is the video number 1. You will have the chance to observe this video also by yourself because Alberto has uploaded the video on the platform. It's a very basic example of liquefaction of the terrain. This is a person, a professor, I think, that is jumping above the ground. And the ground is saturated by water. And this effect of jumping above the ground determines, as you can see from the image, a lack of stability of the ground, a collapsing of the ground, and so a lowering of the capacity of the ground to sustain a load. This is a way, a very simple way to explain to you the liquefaction process. And the liquefaction process is one of the effects, I go back a bit, of the earthquake, because earthquake is acceleration of the ground in motion with a certain frequency, and this motion determines the expulsion of the fluid from the pores, and some materials tend to collapse due to this expulsion of the fluids, and some parts of a landscape are more vulnerable to this process than other ones. And so we can understand before our goal, the goal of planners, the goal of geologists, the goal of engineers is to know the portion of the surface of the earth where there is more probability to have this type of phenomena. And obviously this phenomenon can buildings of bridges and destruction of people, or environments. Let's see also this another video. We are here in Taiwan. I'm sorry, yes, this is the video. There is a very rainy period. We are in a very wet climate. You see on the mountain a lot of water coming out from springs. There is a McDonald's on the right of the street. This person is driving his car along the street. And you see at a certain point, you have a rockfall coming from the slope. Not only small blocks of rocks, but also very big boulders coming from the mountain. And obviously this guy in this car was very lucky, because for a very small amount of space or time, he has not been subjected to a complete destruction from this big block. This is to give you two ideas of my lesson. The first one, the connection between geological instability and intensive rainfall. This is one of the ways how climate change could affect our landscape. And the second one is a very difficult task to predict this type of hazards, because it's very difficult, it's impossible to define the exact location and time where you can have this type of landslide on a street. And so perhaps the best way to cope with this problem, with this issue, is not to predict the exact time and location, but to understand before which are the more vulnerable areas to this kind of phenomena, and to avoid to have streets, roads, transportation system subjected to this kind of events. Also because we know that these kind of events are forecasted to increase in the future, because one of the ways how climate change is going to occur is through the increase of the number of intensive events. So geology is also landslides. Landslide, a landslide, una frana in Italian, is a typical geological phenomenon and is a natural phenomenon, because in the geomorphological evolution of a landscape, it's normal that the gravity addresses all the difference of elevation in the landscape, so tending to go into a lower energy state. And so with erosion, it's a normal process. But if this normal process happens, for example, in a very urbanized area, you have obviously destruction. And so the best way to do it is not to build a urbanized area below a slope that it is subjected to a landslide. So below a slope where you could have a very high hazard of landsliding. Not only so destructive are landslides, but also they appear in a more concentrated and also in plain areas. This is a very recent collapse in Naples, not so many months ago, in a hospital area. And this is another example of ground collapse due often to overpumping of groundwater below. And this is a very famous collapse of a levee of a river, of the Arno River in Florence, very near, you see, to the old bridge, due also in this case to a process of groundwater leakage in the ground that you perhaps to the network, to pipes leaking water in the ground, and with the collapse of this levee. These are other examples of geological phenomena, not only minerals, rocks, fossils, volcanoes, but also landslides in a very urban situation. This is a video in the northern Apennines between Bologna and Florence. You see the Frecciarossa train, also the Italo train in that case, moving, this is a Frecciarossa, moving between Bologna and Florence through the tunnels connecting Bologna and Florence. You know that today, nowadays, from Bologna and Florence and vice versa, with a high velocity speed train, the time is about 40 minutes respect to the 1 hour that needed before. But also this is a geologic problem, because the draining of the groundwater due to the tunnels has determined a drainage of the groundwater system with a desiccation of many springs distributed along the line, and also with the desiccation of the environmental flow of the streams during the summer. And this also is geology. So the impacts of big transportation systems towards groundwater flows. This is another example of geological applications. I don't know if some of you have seen this movie. This is a very famous movie for Hollywood production and for Julia Roberts, because Julia Roberts won the Oscar Prize for this film as Best Actress. But also this is a movie related to a hydrogeological topic, because this is a real case study, a real fact happened in California in the 90s of so about 30 years ago, due to the contamination by hexavalent chromium of some municipal and domestic wells in a small village near Los Angeles, not far from Los Angeles. Also, this is a hydrogeologic hazard. Of landslides is this type of communication. Okay, I go ahead. What about global warming? I know that Antonio Navarra has made for you a lesson before. Veronica Rossi has talked to you about the climate of the past. And actually, we are suffering what we call global warming. So the increase of temperature at a very high rate, absolutely abnormal, not normal respect to what it is naturally expected. Also, this could be considered a geological process, a planet scale process, probably in some way induced by man. We know that the CO2 concentration in the atmosphere is increasing very much, and we see the concentration of CO2 from the half of the 18th century to nowadays. And for example, in 1 century, the concentration of CO2 is increased so much with a very high rate. And this is the same rate where we observe the increase of atmospheric temperature. Also, drought is a hydrogeological hazard. The opposite of intensive rainfall, the opposite of flood, the opposite of tsunamis, where you have a big quantity of water that it is impacting along the coast, or in hurricanes, for example, or a flood in a river valley. Drought, the lacking of water, is another hydrogeological risk, particularly if these droughts are very intense and prolonged in time, also during different years. And you can have a very strong problem about that, because the surface water is the first one. This is a photo, an image of the Po River some days ago. So in a period where in some places you could cross by walking, not by walking, but almost by walking the Po River. Now we have some rainfall in the recent days, but you know that in northern Italy, we are suffering still a very intense drought effect. So basically, we can have natural geological hazards, seismic, volcanic, floods, landslides, and droughts. Generally speaking, landslides and droughts, so too much water from one point of view, too few quantity, too poor, too little quantity of water on the other side are called hydrogeological hazards, dissesto hydrogeological. And we have also man-made geological hazards, like, for example, pollution, because pollution happens below the ground, so happens in a geologic material, in a geologic medium. We have to consider this equation. This is very important. This is the risk equation. I don't know if you already have considered this equation. This is an equation that basically is useful for each type of geological hazards we are dealing with. And we have that the risk is the expected damage that we could suffer from a certain geological hazards, is a parameter, and basically is a probability outcome. So the risk is a probability concept. How is the probability that a certain hazard with a certain intensity could determine against myself or against the people living in a certain area to have an undesired effect? What is this probability? This probability is the risk, the expected damage. Obviously, the risk is related to three indicators, to three parameters. The first one is the hazard. In Italian, hazard is pericolo. Is related to the hazard, so the severity of the event. For example, the size of a landslide, the velocity of a landslide, or the toxicity of the contaminant, or the velocity of an avalanche. This is the hazard, and also the probability outcome of this hazard. Then you have the capacity, your capacity, and the capacity of the society to be defended against this hazard. So the vulnerability. The society is low vulnerable to the hazard if the defense capacity against the threat is very high. And so there is a good protection against the hazard. And finally, you have the value of the receptors. What is the receptor? Receptor or target is the target of the impact. People, citizens, socio-economic activities, transportation systems, industries, all the activities of the environment, ecosystems are all receptors. How much is the value of the receptors in a certain area? So taking into account the exposure value, the vulnerability, and the intensity of the hazard, you can evaluate the risk. Your risk is acceptable or it is not acceptable, depending on the situation we are dealing with. And this, in the next slide, you see the definition of all these items that I have defined now: intensity, hazard, vulnerability, exposure of receptors, and finally, the risk. This terminology, this type of terminology, you can apply to all types of geological hazards that we have considered up to now. So, including hydrogeologic instability, landslides, or groundwater pollution, or groundwater droughts. An example, very simple. You have a baby, and this baby can be wandering in a kitchen where you have a boiling water above the fire, and the baby is not, there is nobody that is going to surveil the baby. So the baby is free to move himself or herself in the kitchen. This is a problem of evaluation of the risk. What is the probability outcome that the baby could be burned by the boiling water? 0, no possibility. 1, maximum likelihood. that the baby is to be, and obviously this depends on the hazard, how big is the pot of boiling water, how hot is the boiling water, and the vulnerability. For example, how is the distance between the boiling water and the baby? How much high is the position of the boiling water? And also the value of the receptor, because the baby is not a wise receptor, so the probability that the baby could arrive very near to the boiling water is higher. And the risk is the output of the hazard time vulnerability time the receptor. And probably in this case, the best thing to do is to avoid that a baby could wander freely in a kitchen with a boiling water pot. And so to eliminate the possible connection between the boiling water, the landslides, for example, with the possible receptor. Some examples in the next slides of the different concepts of geological hazards I have underlined before. Landslide. If the landslide is the event, is the geological hazard, the hazard of the landslide is a measure due to the mass, how big is the landslide, the volume of the landslide, the speed of a landslide. More high is the speed, more difficult is for people to escape from the landslide, so the hazard is higher. Many of you has probably seen on some documentary or movie about the big Vajont landslide that happened in 1963 in Belluno province in northern Italy. I recommend all of you to see some interesting documents and videos and documentary about this landslide. This is a very good example of the unpredictability of extreme geological events, because this landslide was very big in volume, but overall it was very rapid in terms of motion of the movement of a landslide. About 100 kilometers per hour of a very big portion of the mountains went down to a reservoir and determined the casualties and the destruction of Longarone village with more than 2,000 people dead for that. This landslide, it was a geologic phenomenon induced by man, induced by the construction of an artificial reservoir. But it was so unpredictable, the speed of this landslide. And for that reason, the best way to not to repeat an event like this one is not to try to understand the time where we can forecast such an event, but to avoid to build houses or to design a reservoir near a slope that we know is at hazard of landsliding. These are some examples of news about groundwater contamination. I have reported before the example of Erin Brockovich in the case of the movie of Julia Roberts, but we have many examples also here in Italy, Terra dei Fuochi, or some other contaminated sites in Italy where we have a geologic phenomenon, hydrogeologic phenomenon, the transport of contaminant into the ground with the exposure of people to this contamination. So basically, many of these geological processes are unpredictable in the sense that it's very difficult to define the exact time and location of happening of these events. But we can observe the landscape, we can study the landscape, and we can say which are the places of the landscape where it is more probable to have a landslide. We cannot say when, but we cannot say there is more probable than in other parts. And so we can avoid to build something below the slopes that are more exposed, are more prone to landsliding. You see here also, if you are not geologists, you see in these examples that some part of these rocks are prone to fall due to the erosion. More destructive is an event, less probable is the outcome of this event, but when this event happens, you have a big destruction. These are the main earthquake events happened in the past with the magnitudo, so the intensity of the earthquake on the y-axis, and going up to now the more intense earthquake happened in Chile in 1960, more intense recorded by man, obviously, and with a magnitudo of about 10. And you see other famous earthquakes happened in the past, also put in relationship with some important Italian earthquake happened in the past. The most destructive and intense was the earthquake of Messina in 1908. But also in this case, if an event is less probable because it's more destructive, you have, by the way, to not to simply try to forecast the event, but to build better the houses and the infrastructures in order to be able to resist to the event. And this is a problem of vulnerability, to decrease the vulnerability of the system, improving the building way and the building quality of infrastructures. What about intensive rainfall events? This is a very interesting representation relative to Emilia-Romagna region, so relative to our region, to this region, and this is the trend of intensive rainfall from 1990 to 2018, so to nowadays, more or less, which is what is considered as an intensive rainfall event, an event with a rainfall rate higher than 30 millimeters per hour. And you can see here in this graph the number of rainfall events registered in different years and in different days from the rain gauges network in Emilia-Romagna region, the rain gauges network of Arpaio. You see on the horizontal axis the years from 1990 to 2018, and in the vertical axis the days of the year from the 1st of January, the day 0, to the 31st of December, the 365 days. And what we are observing, that moving from the left to the right, the size of the bubble is proportional to the number of events. From the left to the right, the number of events is increasing, and they are most distributed in a certain period of the year between the end of summer and the beginning of fall, where you have the more high contrast of air masses in the atmosphere between warm air masses and humid air masses, with the increase of many important rainfall events. But if you have an increase of rainfall events, you have two outputs. The first one, increase of landslide risk, because landslides are related to intensive rainfall events. And the second output, if more water is falling concentrated in a very short period of time, much of this water is flowing over the surface and less quantity of the water is infiltrating into the ground, contributing to the recharge of groundwater. So you have, from one point of view, an increase of hydrogeological instability, and from the other point of view, you have a decrease of water resources in the groundwater. So you not only increase the risk of landslide, but also you increase the risk of drought. Also, if it is apparently, it seems a strange thing, but an increase of intense rainfall event could contribute to an increase of the risk of drought, because you have lower quantity of water recharging the groundwater. What about vulnerability? Vulnerability could be also related to the capacity of men not to exacerbate or increase the natural tendency of slope to fall to the low elevation. You see here, for example, you have a slope with a house at the top of the slope. And if you make some excavation, for example, to build up a road or some other engineering activities, you lower the resistance of the slope to remain stable, and so you can induce a landslide. In this case, a landslide, that is a natural phenomenon, is exacerbated. The risk of landsliding is increased by the activity of men, because the activity of men has decreased the capacity of the system to be defended, and so has increased the vulnerability of the system. Or, on the other case, you can increase the load of the slope to the top, building some houses at the top of the slope, and then you can have a landslide due to the instability induced by the construction of building at the top of the slope. Two examples of the increase of vulnerability by human activity. Also, in relation to vulnerability, some places are more vulnerable to other ones with respect to vulnerability of pollution. Why? Because the contaminants from the ground surface infiltrate down to groundwater. But in some places, this infiltrability is more easy. In other places, is less easy, because you have, for example, low permeability layer of geologic material in the ground. So if you have to build industrial sites or potentially contaminating activities, you make better to build up these activities where the terrain are less vulnerable to pollution, and not to build these activities where the terrain are more vulnerable to pollution. So if you can't avoid that the contaminant could go into the ground, you can alleviate, can lower the effects, taking into account the different vulnerability degree of the system. This is another example of how you can coexist with geological risk, taking into account the vulnerability to pollution. What about the exposure, so the receptors? Landslides is a natural phenomenon, but they can occur in completely different settings. If you are hikers in Dolomites or in mountain areas, you probably observe these spectacular landscapes with the mountains, and all these deposits of debris at the base of the mountains that are due to basically landslides process, because the debris are eroded from the cliffs of the mountains and are accumulated at the base of the reliefs by a gravity-driven process. But if the gravity-driven process is occurring in a natural landslide, in a natural landscape, there is no problem. But if this process is occurring where there is a big transportation system, you can have this type of effects. And so you can know in advance if you are building big transportation system in areas that could be exposed to landslide. That is a natural phenomenon. What about pollution? We drink water and we breathe air. But if we drink water of a contaminated groundwater, like the citizens in Hinckley, California, in the example of the movie before, or you live in a contaminated ground where vapors from contaminants can rise up to the surface and you can breathe these vapors with toxic effects against your health, you are suffering effects of another example of a geological risk. And also in this case, we have to avoid that people could drink water or breathe air in areas that we know are exposed to contamination. This is a map of Italy where you can see all the contaminated sites of national interest are the most important contaminated sites in Italy. And obviously each of these sites could pose a problem of the threat for potential effects against human health and ecosystems. Finally, the risk. The risk, as I have told to you, is the output of hazard times vulnerability times exposure. If we have a high hazard probability, if we have a high vulnerability, and if the receptor is a high value receptor, the risk is very high. If the risk is very high, we can solve the trouble in these three ways. One way, we eliminate the hazard. It's not so simple in many instances because it's very difficult to eliminate the possible outcome of a landslide. Yes, we can manage the slope, drain out some water, make some intervention, but it's not so easy in many cases. B, to increase the defense capacity, so to decrease the vulnerability, building better the houses or make some defense to the hazard. Third, to improve the quality of the receptors. For example, not permitting that high value receptors live in a slope that we know it is exposed to landslide. So the baby cannot walk freely in the kitchen, otherwise the baby is exposed to the burning. But the climate change is increasing some type of geological hazard, in particular related to water, so hydrologic events, landslides, and droughts. And we are suffering an increasing of global economic losses from climatic hazards. You see that in the last 40 years, the losses from weather disasters worldwide are increasing because are increasing main hydrological events and are increasing droughts. And this is determining an increase of economic losses. So it's very important also for economy, not also for the casualties that are related to this process. Okay, this was the first lesson about the general definition of geologic hazards. Now I'm going to the lesson number 2, that along with the lesson number 3 is the, because I'm concentrating my teaching on 2 types of geological hazards in relation to climate change, landslides and groundwater flow. Landslides on the left, groundwater on the right. For both of these, I will describe in a first stage the natural process, because I would like to give you some idea of how landslides occur and how groundwater flow below our feet is occurring. Then we will see the effects of climate on these 2 processes, geomorphological one, the landslide, hydrogeological one, groundwater flow. Then the impacts by climate change acting on these 2 processes. And then the problem of assessment or forecasting, mitigation, so trying to mitigate the effects, and adaptation, so to adapt ourselves to this modification. Let's begin with landslides. Landslides are a variety of examples of processes and phenomena. And we have already seen, this is the famous landslide of Vajont, seen from another perspective. This is another very famous landslide in Italy, in Valtellina, the Valpola landslide. And this is a typical example of a ground collapse. Are all examples of geomorphological hazards, where due to the big occurrence of water in high quantity, you have at a certain time an instability, and the instability transforms the slope in a landslide. This is an example of a landslide. Also, if you go around the landscape, you drive the car and you walk in the landscape, you observe sometimes this scar in the relief due to some phenomena of geomorphological instability. This is the landslide of La Conchita in California, but when we observe, this is the same landslide as the picture before during the outcome of the landslide. And it is a very destructive phenomenon occurring in a very short period of time that in this case has not involved buildings or roads, but you can imagine the effect if this outcome could impact against buildings or roads. We have another example in Italy. We are in Calabria here in Maierato. Maierato is located in Vibo Valencia area in the southwestern of Calabria in February 2010. There is a very long movie that perhaps some of you have seen also in the TV with an enormous quantity of rocks and sediments moving down from the slopes. If you see the video that you can download from the platform, you can see the voices of the people, all these people here that are observing this process. Obviously, it's very incredible because you see that the movement of this big quantity of rocks, trees, earth are moving in a very fast way due to intense period of rainfall immediately before the landslide. Take into account that these big landslides is not so speed in velocity like the Vajont landslide. The Vajont landslide had a speed of about 100 km/h. So it was absolutely impossible to register it like we are observing this landslide. Basically, there are 5 types of landsliding that can occur in the system. And now I'm briefly describing it, examining their process. The first one, we have to consider that all these landslides could involve 3 types of material: rock, debris, and earth. Rock is a piece of rock, also very big piece of rock that could be involved in landsliding. Debris, detrito in Italian, is smaller pieces of rock, but with a dimension, with a size higher than 2 millimeters. So from gravels to pebbles, cobbles, blocks, pebbles, ciottoli, ghiaie, or blocks of rock, quindi blocks of a big size. Earth, that we can translate in Italian terra, is made up by finer particles of rocks in the dimension of a sand, like the sand of the beach, so between 2 millimeters and 0.06 millimeters, silts, clays, and peat. Peat if the organic part, peat is torba, if the organic material is prevalent. So you can have these types of movement, 5 types of movements with different destructive capacity from fall. We are going to describe and observe it in a detailed way in the next slides. And these 5 types of movement can involve 3 types of materials: rock, debris, and earth. And so you can build up a table with the type of movement on the vertical axis and the type of material on the horizontal axis. So for example, you can have a slide debris when you have a slide as a type of movement and the debris as the type of material. Let's observe the different types of movement, starting from one important point. Why do we have a landslide in a certain place in a certain time? You have to imagine that along the slope of the mountain, generally, when there is no movement happening, because you are in an equilibrium situation, all the slopes are subjected to gravity that tend to make the slope moving toward the base of the slope itself. And these forces are the so-called destabilizing forces. But on the other hand, you have resistant forces that avoid to have this movement. And these resistant forces are due basically to the cohesiveness of the rock and the material. So the way how the different particles of the rocks are held together, and also the internal friction due to the currents of the water. And this is very important, water, because the water is related to climate change. And so climate change, intensity of supply of water to the surface, landslide, because an increase of the water content, of the material, increase the water pressure inside the material, lower the internal friction of the material, and so lower the cohesiveness of the material. And lowering the cohesiveness of the material, you have an increase of destabilizing forces. And so you have the capacity of the slope to fall down. So too much water, it implies more instability. If I want to stabilize a slope, I need to drain out water from the slope, so lowering the probability that the slope could fall due to instability. Let's observe the 5 types of movement. Fall, crollo in Italian. It's very simple. You have a very vertical cliff in the rock. This cliff is subjected to erosion, for example, to heating, to the ice, to the rainfall, to the erosion, and different blocks of rock are detaching from the cliff and are going down by gravity to the valley, by fall, by bouncing, by rolling, with different size of these blocks. And these blocks could be very big in order to be able to destruct a building like this one. We have seen before the movie in Taiwan with the big block arrived to the street. And you can see from this picture the high unpredictability of the effects of this type of landslide. In this case, we have a rolling stone, a very big rolling stone coming down from the cliff. And this rolling stone has completely destroyed one building, and another one near to it, it's not involved. It's a lucky outcome of the landslide, but you can imagine that the best thing is not to understand where the rolling stone is going to pass or when, but probably not to build this kind of buildings below a slope that could be subjected to this kind of landslide. Second type of movement is topple. In Italian, ribaltamento. You have the same vertical cliff, and for the erosion, you have the rotation of the moving mass below a barycenter and the evolution of the block toward the base of the slope. Here you can see a video giving you the idea of this rock toppling of the cliff. You see that this slope is already prone to toppling. There are fractures, and at a certain time you see all the rock is completely falling down by rotation and then by complete disruption towards the base of the valley. Also, in this case, obviously, it's very rare to have this movie because you have to be there exactly in the time where the phenomenon is occurring and avoiding, obviously, to be destroyed by the phenomenon itself. The slump. This is perhaps the most common example of landslide. And the slump is a rotational slide where a block of rock is sliding along a rupture surface that is curvilinear. You can see the curvilinear surface and is collapsing down to the base of the slope. Generally, you can observe this type of landslides for the occurrence of ponding and small depressions in the ground. The tilting of the trees are all evidence that that are outlining the fact that we are in a place of a landslide. It's an active landslide. Imagine to have this situation. This is the slope before the landslide occurring. This is the potential surface of rupture. Along this potential surface of rupture, you can have an instability due, for example, to the occurrence of high quantity of rainfall falling down in this area. And at a certain point, you have the loss of the resistance of the material along the surface, and you have the movement and the formation of the landslide. This is an example. This is another important landslide in Veneto, Tessina landslide in the Belluno area. You see the typical pattern of the soil after the outcome of the landslide. The other, potete fare un po' silenzio per favore, perché si sente questo parlottare, o andate fuori se non siete interessati, oppure state zitti. Vi ringrazio molto, perché poi diventa faticoso anche per me. Grazie. The second type of the landslide is a translative slide. In this case, the surface of rupture is not curvilinear, but it is planar. So it basically it's a plane that has a very defined setting and position along the slope, and you can see the mass of the rock, that it is detached from the original location and it is sliding along the surface. In this case, in order to be able to understand if this setting is able to give the chance to have a landslide, the geological structure of the slope could be favorable to this movement. For example, you can have some planar surfaces that are already present before the landslide. But also in this case, if you have intensive rainfall on the surface and you can have the instability condition happening along this surface, and so you can have the landslide. This is a picture of a typical planar slide along a surface. Fourth type of movement is the spread, espansione laterale in Italian. Basically, you must have a soft material below, like for example, a clay material, a more competent, more rigid material above, and the more competent material above, it is fractured and then begins to move laterally due to the flow of the material below that is softer. Also in this case, the role of the water is very important. This is a spectacular example of rock spread in Sassi di Simone e Simoncello. We are in Tuscan Romagna Apennines, between Tuscany and Emilia-Romagna, where big blocks of rocks, big mountains, has moved very slowly, obviously, due to the fact that they are more rigid and below are characterized by the occurrence of softer material, and so they can move laterally in a very slow way due to this rock spread. And finally, the last type, the fifth type of movement, is the flow. The translation in Italian is colata. This is one of the most dangerous landsliding process, with impact very severe against transportation systems, buildings, and people. And these flows, colata is the name in Italian, are very strictly related to the high water content. So when you have in the mountains this the outcome, the happening of intensive rainfall event, and so the intensive production of rainfall water arriving to the ground, you can have the outcome of these flows. The flows could be earth flow or debris flow. Earth flow is made up by fine-grained material, and they can be more or less rapid in motion. And this is a typical example of an earth flow flowing along a slope in an area in the Campania region. You have to imagine that when there is intensive rainfall, this mass of the slope is moving in a more fast way. Where you are in dry condition, the phenomenon is stopping and then is beginning again when you have a supply of water coming to the ground. But you can have a debris flow when the fragments of the rocks are higher in size, and in this case the debris flow has deposited a very thick material on a river, but this debris flow could be very, very destructive. One of the most destructive debris flow in Italy was the Sarno debris flows that occurred in Sarno in Campania in 1998. And these were very destructive, and there were many casualties and destruction of some villages that were located at the base of the slopes. So we have seen we have described the type of landslides, the type of movements that we see in the landscape. Which are the effects of climate on this process, on the geomorphological process of landslides? Basically, you have to imagine a landslide with like a balance. In the balance, we have two types of factors: geological factors, hydrological factors. And the geological factors give you an answer to the following questions. How I can expect that in a certain slope I observe a landslide? So how is the type of movement and where I expect a landslide? This is due to the geological type of the slope and to the geological structure. Which type of flow, for example, can I have? Earth flow, debris flow. If I have fragments of rocks of higher dimension, I will have a debris flow. If I have a clayey slope, I will have an earth flow. How fast will be this process? All these questions could be related to geological type, but I have also to take into account water. And so how and when I will have a landslide? When I will have, along a potential unstable slope, a high quantity of water arriving to the surface. And how fast will be this process? It depends on the quantity of the water arriving to the surface. So both types of factors determine if the balance is to the right or to the left. If I have too much water, I will have a higher chance to have a landslide of a certain type. Otherwise, I will have a stability condition. And the water content is very important. The water content could be very variable. And you can have a dry material, no water at all. If, for example, you have some dry sand or dry gravel, and you put this sand along above a table, the sand has a certain slope of stability that it depends on the grain size of the sand, a dry sand. But if you begin to to pour water above the sand is going to become humid and then wetted, and then is not able to stay with a height steep and try and begin to flow down due to the increase of water content. And from a dry condition, we go to a humid and then to a wet and then to a very wet. And increasing the water content, you have an increase of the fluidity of the material. And so of the capacity of the material to flow. And so the capacity of the material to move toward the bottom of the slope. In this video that I'm going to show to you, there were a camera located near a place of near a location of a earth flow landslide. And this earth flow landslide, when there is an intense rainfall, begin to move. When you are far from rainfall event, the landslide is blocking, is stopping, and then it is reactivated again by intense rainfall event. This camera is recording the location of the landslide 24 hours continuously, also during daytime and during the night. During the night, you don't see anything because we are in, there is no light that illuminating the scene. But in this movie, there is an acceleration, so you can see different night and days, and you can see the importance of rainfall intensity in moving the system. You can see here, this is the nighttime, this is the daytime, and at a certain point you see the beginning of rainfall, and you see the increase of the speed of the motion of the slide of the landslide. And when there is a decrease of rainfall intensity, there is the decrease of the velocity of the terrain. Imagine that this video could be applied, for example, to this kind of landslide. So if the video is not related to this landslide, it is in Emilia-Romagna, is in another location. But if the video is here on the side of the landslide, you can see the movement of the landslide increasing when you have a high rainfall intensity, and decreasing where the rainfall intensity is lowered. So there is a relationship between the rainfall intensity and the landslides. We can see also another example. Yes, this is an animation. Imagining a slope with a rainfall that has inducing an instability along the potential surface of rupture. And you have, in this case, a slump. So a rotational landslide that, due to the supplying of big quantity of water, as determining a movement toward the base of the slope. You see all the trees are inclined. You see the different steps of the mass of the landslide. And this is due to the effects of the water table that is increasing their position. We will see what is the water table, the water below the ground, and has activated the landslide. Here you can see the same conceptual model of before. This is the water table, the level of the water inside the ground. If you have a high intensity rainfall, the water is infiltrating and the water table is raising up. And if the water table is raising up, you can have the instability situation along the surface of rupture, because along the surface of rupture, there is a lowering of the internal cohesion, of internal friction of the rock. Also in this case, landslide is a consequence of intensive rainfall. Let's observe this video. Here we are in an example of a debris flow. Debris flow, so a flow of material with a dimension, with size of the grains higher than 2 millimeters. Debris flow are very destructive. In this case, the person who has made this video obviously is in safe condition, and the debris flow is occurring inside the valley. So basically it's not acting in a destructive way against people or buildings or bridges. But you see in a very evident way how debris flow is basically a flow of water, very rich of material, with the capacity of transport also big boulders, because the density of the fluid is so high that the capacity of transport of the material is higher than in condition with normal water. Normal water is not capable to transport these big blocks, but a mud, very fluid mud like this one is capable to transport big blocks. And imagine the destructive capacity of a debris flow toward buildings and infrastructures occurring in an area. Also in this case, debris flow is a consequence of intensive rainfall event. And so event of precipitation that induce high quantity of water concentrated in time, arriving to the ground and increasing the water content of material, and so inducing the movement of the debris flow. Another video, another example of debris flow. Perhaps I have. In this case, we don't see anything because the video is not starting, but in the video that I have uploaded to the platform, there was another example of debris flow like this one with a movie registered in the US. Perhaps, yes, perhaps we can start. We see if it runs or not. Perhaps, no. But it doesn't matter because more or less it's the same situation as before. Okay, you will see by yourself the video on the platform. Another important consideration. Landslides can reactivate. You don't have to consider that a landslide happens in one place and that's all, as finished. No, a landslide could happen again and again and again in the same location due to the reactivation of the process. And the landslide will go over in time until all the slope has found its final stability condition. And here is an example in Emilia-Romagna. We are in the Reno Valley, in Gaggio Montano, gradient up in respect to Bologna. And this is an aerial photo. You can see here the mass of an earth flow. So a movement, una colata di terra, a movement of earth, so a material with the size of the grains lower than 2 millimeters, that is moving more or less slowly toward the Reno River that is here in the low valley. This is a photo of some years ago, 18 years ago, but this in 2018, this landslide was reactivated by the intensive rainfall. Then there was some snowfall in this area, and you can see that the landslide has destroyed the street that was passing here and has arrived to the Reno River, in some way obstructing the river course, also not completely. This is another outcome of a landslide. They can invade the river, block, like with the dam effect, they can block the river flows and determining a lake forming upstream of the landslide. There are some works trying to stabilize the situation, and then the slide was stabilized again, and the street was reactivated. But this to give you the idea that landsliding in some way are like volcanoes. Many volcanoes are period of rest and period of eruption, and so landslide in some situation are period of rest and period of reactivation. And their reactivation is related to rainfall intensity. When you have rainfall intensity, you can have the reactivation of the landslide. Last say I would like to say before to make a break is to the Vaillant landslide. Vaillant landslide, sorry for this going back. Oh, yes. Yes, it was in another presentation, but by the way, this is the Vaillant landslide. Vaillant landslide is only one shot landslide, not a continuous process, because in that way, the surface of rupture was completely pristine, was completely natural at the origin. It was the first instant, the first time where Vaillant landslide occurred in that place. Due to the increase of the level of the reservoir, of the Vaillant reservoir, and this has determined a potential, a strong instability along the surface of rupture. It was so speed in velocity, 100 kilometers per hour, because it was the first time that it happened. Generally, the first time that a landslide happens, it's very fast. Then it tries to find another stability, moving more slowly in the following steps. But the first step generally is very rapid. And for that reason, it was very rapid due to the fact that it was the first time that a landslide occurred in that area. And so it was so destructive. But we will talk about the effects of landslide in the Vaillant area the next Monday, the next lessons. I have finished also lesson number 2, and before to start with lesson number 3, I will have a break. If you don't have questions, I'm here to reply to your questions. Otherwise, we have a break for about 15 minutes. Okay? Okay. So we start again in a quarter of hour. Thank you. Prego.
Era fatta apposta quel canale oppure era nel video del debris flow?
Sì.
C'era un canale che poi si è riempito con la colata. Era fatto apposta quel canale per vedere?
No, di solito i debris flow, siccome i detriti stanno a monte e di solito i debris flow si incanalano in valli di torrenti, quindi quello di solito si incanalano le incisioni. Quando non sono giganteschi, bene o male si gestiscano nei canali, quindi poi si depositano anche sotto i ponti, dipende da quanto grossi sono. Certe volte quando sono troppo grossi esondano ovviamente dal canale, spaccano i ponti e vanno a distruggere le abitazioni. Se sono meno intensi, perché c'è una minore quantità di acqua, sono contenuti, allora li puoi anche osservare, che di solito quando l'evento meteorico forte è a monte, certe volte non piove nemmeno a valle, ma sta piovendo molto a monte, e poi tu lo vedi arrivare e in questo caso fai un filmato ma non ti succede niente. Dipende dall'intensità.
Poi un'altra cosa, nella slide dove erano presenti i rifiuti a livello italiano,
i siti contaminati di interesse nazionale.
SIN, come unità di misura.
SIN è sito di interesse nazionale. E quelli sono dei grossi siti, di solito sono zone industriali di vecchia storia, che sono molto contaminati e in cui il Ministero dell'Ambiente mette delle risorse per le bonifiche. Sono le zone, diciamo, più contaminate e conosciute in Italia.
Grazie.
Prego. Prego.
Non mi è molto chiaro, cioè la frana è dovuta quando c'è troppa acqua. Quando il terreno
La frana spesso avviene quando c'è di mezzo dell'acqua che aumenta l'instabilità.
Ma se invece siamo nel caso di siccità, che c'è poca acqua, può comunque verificarsi una frana o no?
Difficile. Allora, l'abbondanza di acqua genera il fenomeno franoso in generale. La rarità dell'acqua, seccando il terreno, in qualche modo lo stabilizza. Cioè, tieni conto che, per esempio, per stabilizzare una frana, tu devi eliminare l'acqua, no? Fai dei drenaggi, la allontani, perché se la allontani, la stabilizzi.
Ok, poi pensavo che anche nel caso in cui ce ne fosse troppo poca, magari non so, si sbriciola.
No. Di solito la roba secca alla fine tende a stare più stabile. Un altro motivo di instabilità che non è legato all'acqua è legato per esempio al riscaldamento della roccia, cioè se la roccia di giorno si riscalda, di notte si raffredda, di giorno si riscalda, di notte si raffredda, se ci sono delle fratture a forza di questo movimento di dilatazione e compressione, un pezzo di roccia può venire giù, certe volte succede, cioè giornata perfetta, luminosa, non c'è nessuna pioggia e ti arriva giù un pezzo di roccia. Però in generale la mancanza d'acqua stabilizza. La mancanza d'acqua stabilizza. Prego.
Dov'è lei, Prof?
E sono di Firenze.
Firenze. Io sono di Sesto.
Ma dai.
Sesto Fiorentino.
Ma sei qui per fare...
Faccio ingegneria meccanica. Lei ha tanto che...
No, io sono qua da... Prima ero a Ferrara. Sono sempre stato in Emilia Romagna. No, sono 10 anni che sono qui.
Ma ha studiato a Firenze oppure?
Sono a Firenze. Ho fatto il dottorato a Firenze ormai tanti anni fa. E poi Ferrara e da Ferrara a Bologna. E tu fai pendolare?
No, c'ho la casa qui adesso. Ho fatto 6
cioè,
mesi pendolare, primo anno, poi basta.
Sei riuscito a trovare una location?
Sì. Sono qua vicino, sono comodo.
Sì, a parte il fatto che ora ormai il treno è diventato anche fattibile, però è costoso. E poi comunque è meglio starci.
No, è troppo tempo che perdi. Cioè, io devo fare il cambio a Prato, poi
devi fare il cambio a Prato.
Cioè, tornare sempre di
No, è molto meglio stare. Sì. E come mai Università a Bologna e non a Firenze?
Perché tu volevi... Firenze, sì, volevo anche fare la vita.
Però uscire, sì.
Ingegneria a Firenze non è
un granché. No, vai fuori. E fai meccanica? Bene. Poi qui per motori sono forti.
Sì, quello sì.
Professore, scusi, una domanda da casa.
Prego.
Sì, volevo, non so adesso se lei può aiutarmi, volevo sapere per quanto riguarda gli obiettivi del corso, cioè il corso sarebbe aperto anche per figure diversi da noi ingegneri o solo per noi?
Ah, dunque, siccome questo è considerato una soft skill, è chiaro che è aperto a tutti gli studenti Unibo. Cioè io sto cercando e credo ai miei colleghi lo stesso di dare come dire, una formazione di base, cioè non eccessivamente specialistica, in modo tale che anche persone non formate sugli aspetti, in questo caso geologici, siano in grado di comprenderlo. Quindi credo sia aperto a tutti, non solamente a... Tu di che formazione sei?
Scrivo, cioè, come ingegnere chimico.
Ah sì, cioè, volendo sei anche più attrezzato di altri, perché quantomeno sugli approcci quantitativi sei sicuramente più formato di altre figure che al limite possono seguire aspetti più umanistici o economici o giuridici. No, no, per me, cioè, le soft skills sono create apposta per andare bene a tutti, cioè a qualsiasi tipo di profilo.
Perfetto, grazie professore.
Prego. Come? Sì, mi ha detto Alberto Montanari che le ha caricate lui. Se ancora non l'ha fatto, dopo glielo ricordiamo. Perché io gliele avevo mandate tutte a lui già 2 giorni fa e lui mi aveva detto che le avrebbe caricate lui. Quindi se... Perché il docente ufficiale del corso è lui, quindi ora... I think we can start. We can start the second part of this lesson. So I begin again. And I will concentrate myself in these last 45 minutes on groundwater. We have seen the geomorphological process of landsliding, and basically it is a process that is acting at the surface. and it is due basically on the instability of the gravitational movement of the ground. But we have also to know what's happening below the ground and how water is flowing below the ground, because this is very important, because you will see the next lesson, the next week, how it is important groundwater for climate change and for the adaptation to climate change. So basically now I'm going to talk about the water down under, the water below the ground, the groundwater. Whereas the landslides are a phenomenon that you see because it is at the surface. So we have an experience of what's happening at the surface. And about water resources, we have an experience about the rivers, the lakes, the glaciers, the rainfall, because it is at the surface. But we don't have any experience of groundwater because we don't see it. We don't see the phenomenon below. But it's very important. Why it's very important? Because if you reflect upon this simple data, you can imagine the importance of groundwater. Basically, reflect upon this fact. In our planet, about 97% of the water is salty water, is ocean water. And if an observer in the space observe our Earth, our Earth has a blue color due to the oceans and due to the big quantity of ocean water. Only 3% of all the water in the planet is not salty, is fresh water. But if we take this 3% and explode the bar to the right, you see that of these 3%, the majority, about 3/4, 77% is ice, is solid water, concentrated in the ice caps, Antarctica and Arctic regions, in the glaciers, in the mountains, in the icebergs. And only 1% of this 3% is surface water. So the lakes, the water in the atmosphere, the rainfall, the clouds, the soil moisture, the water in the soil. And look to the rivers. Rivers like the Po River, the Reno River, the Mississippi River are a very thin fraction of this thin fraction of this thin fraction. Finally, the most abundant quantity of fresh water available, because liquid and not solid, is groundwater. That it is about 22% of this 3%, much more abundant than the surface water. But we don't see the groundwater because it's below the ground. But probably from reflecting upon this data, you understand that if in the future our planet is going to suffer some problem of drought, aridity, and lacking of water at the surface, one possible way to react to this problem is to base our development on groundwater, the water below the ground. Another value, consider the proportion between the groundwater occurring also in the first 750 meters of depth below the ground. So the shallowest part of the crust, of the continental crust. For each liter, you imagine to have a bottle. This is not 1 liter, but to give an idea, for each liter of surface water, you have 33 liters of groundwater. And in this liter of surface water, you have the rivers, the lakes, the rainfall. And in the 33 liters of groundwater, you have all the water below the ground. So it's very incredible, this value. And we have to reflect upon this, that the highest quantity of liquid water is below the ground. It's not above the ground, it's below the ground. Why there is so big quantity of water below the ground or in the rocks? Because the rocks and the sediments are full of voids, are porous, are not completely solid. And so, if they are porous, you have to imagine the rainfall falling to the ground, the water is infiltrating into the surface of the ground, and it's permeating the pores in the rocks and sediments. So you have to imagine that due to the porosity of rocks and sediments, there is the chance that water can fill these pores, forming groundwater. If you are not a geologist, and when somebody asks you how you imagine the water below the ground, probably you imagine these pictures: caves, big, enormous locations, like the famous story of the journey to the center of the earth of Verne, a location where pioneer people travel through spectacular stalactites and stalagmites inside the caves. Yes, obviously, caves are actual important parts of the subterranean world, but basically this is very particular setting, very rare, very specific. But for the most part, the porosity is not due to the caves, but it's due to another type of formation. We can have two types of pores: primary or interstitial, and secondary or due to fracturing. Imagine particles of rocks deposited by rivers, for example. Imagine this picture. They seem potato, but they're not potatoes, they are sands. Sands are fragments of rocks of size about 1 millimeter. So imagine that each of these fragments is made up by 1 millimeter, 1.5 millimeter, 2 millimeters size. And these sands are deposited by a river, for example, or by the waves of the sea along the shore. And when these sands are deposited, between each particle and the other one, you have voids. These voids are called pores, pori in Italian. And these pores could be filled by water. And the dimension, the size of these pores is the same size than the size of the sands. So if the sands have size of 1-2 millimeters, also the pores have size of 1-2 millimeters. So we are not talking about caves of tens of meters of size, but we are talking about very small pores. And all these pores are connected together. And groundwater is flowing inside them very slowly in a very big volume below the ground. That is groundwater flowing phenomenon. How much is this porosity? Imagine this situation. Imagine to take, for example, bowling balls. And you fill completely this classroom with bowling balls. So balls more or less of this size. And you put these bowling balls all above each other in this setting. And you imagine to fill completely these rooms, this classroom, with these bowling balls from the floor up to the ceiling. Between these bowling balls, you have pores. How is the fraction of these pores with respect to the total volume of the classroom? In your opinion, how much is this fraction in terms of percentage? About 80%, about 50, about 20. Yeah, a bit lower than 50. It's about 40% of spores. If all the particles are spherical, and if they have a pattern of distribution of this type. If imagine that these particles could be sand grains that are not completely spherical, but are similar to spheres, like this one, you have an idea that about 40% of the subsoil is porous, is void, is not made up of solid. And so water can be flow inside it. And so can be formed a very big quantity of liquid water below the ground. It is independent of the size, because if you fill this room not with bowling balls, but with glass beads, for example, biglie di vetro, the distribution of the porosity is the same. You have the same percentage, the same fraction of voids respect to the solid. Obviously, if the fragments of rocks, and so the spheres, are distributed in this way, more packed, the porosity is lower, is about 20–25%, not 40%. But it's a good quantity, it's a good value. Not all sediments are porous, because many of them are cemented. So you have the cementation, the production, the precipitation of cement. This cement could be calcite, calcite, or quartz, can precipitate and so close up the pores. In that case, the porosity is going to decrease. And so you have lower porosity than before. But rock that are not porous, because are completely solidified, could be fractured. And why? Because for the tectonic forces of the crust, the rocks normally fracture with faults, faglie, or fracture, fratture. And this fracture could be location of groundwater flow. This is the second type of porosity, fracture porosity, and not interstitial porosity. This one is the interstitial porosity, and this is the fracture porosity. So, more a sediment is porous and more a rock is fractured, more groundwater is able to flow inside it. But this is the capacity of a rock to store the water in the pores. But there is also the capacity of the rock to move the water. The first of these property is called porosity. The second of these properties is called permeability. Permeability is the capacity of the rock to be crossed by water, to be crossed by water. So the water has the capacity to flow inside this rock. From what depends the permeability? I give you a very extreme examples, but I think that's very useful for you. This type of rock is very typical of volcanic areas, and we call in Italian pomice, in English pumice. It's typical of volcanic eruptions, and it's very light, this rock. If you throw on the water, it floats on the water. It's not sink down. Why? Because it's very porous. It's full of bubbles. Because when this type of rock cool down from the volcanic explosion, it becomes like a sponge. But these bubbles are not connected between each other. So these rocks could not be permeable. It's very porous, but not permeable, because the pores are not connected between each other. So porous, but not permeable. On the other hand, we have a clay. A clay is a rock, is a sediment, made up from fine, very, very fine grain materials, lower than 2 microns. 1 micron is 1/1000th part of a millimeter. The clay are made up from fragments lower than 1 micron size. The pores are very small, but are interconnected. But the water inside these pores, is not moving because the pores is attracted from the surfaces of the clay, and it's not able to move because the electrostatic forces are dominant respect to the gravity ones. So in the second case, the material is very porous, but pores are not permeable because are very small. So in this case, pores are not good for permeability because are not interconnected. In this case, pores are not good for permeability because are interconnected, but are very small. What is the ideal condition? A sand. Because a sand is made up by pores, interconnected, and rather big in size to permit the groundwater flow. So the sand is a good, as we can say, and you will see the definition in the next slides, an aquifer. So a geologic material capable to store the water and make the water flow inside it due to the interconnection and good size of the pores. And this is important because if you find an aquifer below the ground, you drill a well and you can exploit the groundwater from this sand because it had a good capacity to make the water flow. But there is another interesting phenomenon in geology that increased the permeability, and it is called karst. Karsismo in Italian. What is karst? Karst is a German term derived from a Serbo-Croatian term, because many of the terminology of the karst system born in the karst area between Slovenia, Croatia, and Serbia, and is due to the fact that rocks are subjected to dissolution. Why? Because many rocks could be, during the groundwater flow, the groundwater acts like a dissolving agent. The ions of the rock go in solution, And so the groundwater flow increased the size, progressively increased the size of the fractures of the rocks. And this process is called corrosion. And with the development of this phenomenon, you have the formation on the surface of doline, that are depression in the ground, sinkholes, inghiottitoi, that are deep holes into the ground, and many conduits and caves, condotti e caverne, that are due to this corrosion. Streams, surface water, are missing at the ground, and all the groundwater is active below the ground. The rock is like a groovier, the cheese groovier, full of holes connected between each other. Which are the factors affecting and producing the calcification? You need rainfall, so you need the quantity of water coming from the sky. You need carbon dioxide dissolved in the water, and this carbon dioxide is coming from the microbiological activity in the soil. You need soluble rocks, like for example, limestones, calcari, or gypsum, jesse, and time. And you have the formation of very important karst system. They are fundamental for us. For example, Rome, capital of Italy, the main source of the aqueduct of Rome is a spring called Peschiera Spring that is located in the central Apennines in Latium, in a karst area. Due to the karstification of the limestone, you have the formation of a big groundwater circulation with a spring so important that it is able to give the water to a big city like Rome. This is an example you can see here of the karst massif, of a karst massif, un massiccio carsico. From the infiltration, from the rainfall, you have the swallow holes, the sink holes developed in a vertical pattern, and then you have horizontal flow in these big conduits toward the outlet of the system to the base of the system. You see that all the rock is completely involved in this karstification, and so with the formation of a very active groundwater flow system. So we have definitions in hydrogeology. An aquifer is a rock or sediment able to transport the water from ferro in Latin, ancient Latin, to transport water. Example of aquifers: sands, gravels, karstic rocks, fractured rocks. And then we have other type of material, less permeable. For example, aquitard, from tardus in Latin, that it means slow, where the water is moving but very slowly. For example, silt or mud. Or aquiclude, so low permeable because the pores are very small and the water is not capable to flow inside it, like for example a clay. And the aquiclude derives its meaning from claudere, that in Latin the meaning is close up, to close, to sigillare, to seal the movement of the water. So aquifers are very important to exploit the groundwater for the ground. Aquiclude are very important to protect groundwater from the contamination from the ground. In the first lesson, we have introduced the concept of vulnerability. If an aquifer below the ground is well protected from contamination, it has some low permeability material above that protect it from the contamination. And so the distribution of aquiclude and aquifer, it's important to understand the vulnerability to the contamination of the aquifers. This is the definition of the aquifer in hydrogeological terms. Is a saturated, so full of water, fill of water, permeable geological unit, capable of transmit meaningful quantities of groundwater in natural conditions. This is an expression of the permeability. We call this coefficient hydraulic conductivity or coefficient of permeability. And these are examples of good aquifers: sands, gravels, fractured aquifers, volcanic aquifers, and karst systems. So, if you want to exploit groundwater, you need to drill a well in an aquifer. And the aquifer is made up by sediments with a good connectivity of the pores, or a rock with good fracturing or karstification degree. Whereas the aquifer below is made up by less permeable material. And so if you want to exploit groundwater, you must rely upon this aquifer material. If you want to protect groundwater from the contamination, you must rely upon this aquitard or aquiclude material. How do we exploit groundwater? By two ways: wells and springs. Wells are drilling, are perforation inside the ground, made up by hand. Generally, in these areas, there are the possibility to dig wells by hand until few meters below the ground, and tapping the water by hand-operated pumps. Or they can be drilled by mechanical system, arriving to hundreds of meters below the ground and capable to produce a high quantity of groundwater. So to catch up, to take out from the ground the water, the groundwater, we need to drill the wells until the aquifer, put in the hole a pump, and exploit the groundwater, taking out the groundwater from the ground. On the other hand, we can have a spring. A spring is a natural setting where the groundwater is naturally flowing out from the rock, where there is a location and a structural setting that permits this outflow. You see in this very simple scheme, imagine to have the rainfall falling to the ground is permeable, so the water is infiltrating down. At a certain point, you have an impermeable rock material below, an aquiclude. Above this impermeable rock, you have the formation of a groundwater flow. The groundwater flow is flowing below the ground, and in a certain location, it discharges out, it outcrops out of the ground, forming a spring. And this is an example of a spring. Here, I let you see some examples of springs in Emilia-Romagna. This is the most important spring in Emilia-Romagna region. It's a natural spring. It is called the Poiano Spring. We are in the Secchia watershed in the province of Reggio Emilia. This is a very interesting and spectacular ecosystem setting with the total discharge of around 150-200 liters per second. This is the most important spring in Emilia-Romagna. This is a natural one. Many others are uptaken for groundwater supply. This is another important spring, always in the province of Reggio Emilia, Collagna, in the upper watershed of Secchia River. And imagine that this is a tunnel drilled inside the rock. And from this tunnel, they uptake a big quantity of groundwater with a discharge around 100, 120 liters per second. And this on the left is another important spring not far from here in the municipality of Zocca in province of Modena in the Panaro watershed. This is the Nadia Spring, is another important spring in the Northern Apennine, the biggest spring between the Bologna and Modena Apennines. Coming out from the rock, you see a very important tunnel excavated into the rock, and the water is arriving into this tunnel, and then it is transported out to the aqueduct with the discharge around 50, 70 liters per second. These are ways to produce groundwater by wells or by spring flow. Spring could be considered both from a hydrogeological point of view or from an ecological point of view. From a hydrogeological point of view, springs are places where groundwater is exposed at the Earth's surface, often flowing naturally from the bedrock. And whereas if you can consider also the ecological value of a spring, because often springs are spots of biodiversity, where biodiversity is very important, because are a transition zone between the ground and the surface, and the presence of groundwater is a good factors making the high development of high quality ecosystems. Basically, a springs functions like this one. This is the springs. This is a very big tank filled with water with a certain level. And the springs is the location where this big tank is going to be depleted by the spring flow. Obviously, the tank is never depleted because you have the rainfall coming from above, continuously replacing the water that it is discharged by the spring. But climate change, we will see, can affect this process with the lowering of the recharge, and so with the lowering of the discharge of the spring. An example, you walk in this pathway. We are here near Montebaldo, near the Garda Lake in northern Italy, and you observe this cliff of rock on the left, and you don't see any water. We are here in a period, very prolonged period of no rainfall, so of dry condition. And you don't see any water coming out from the rock. But if you walk in the same pathway, in the same location, after a severe, intense rainfall, you observe this phenomena. You observe groundwater discharging out from the rock. These are two examples of springs where groundwater naturally is flowing out from the rock. This is a hydrogeological process, and you have to imagine that in some way the rainfall is infiltrating in the upland of this rock massif, and then for the structural setting of the rock is discharging out by the springs. Also, snowfall is very important for springs, and this is another connection to climate change. Here we are in the western part of the Alps. We are in the Piedmont region, and you see a very snowy landscape during the winter, and we don't see any water coming out from the rock. This is a limestone, so it's a very karstified rock very permeable for the calcification. But when the snow melts down from the same location, we are obviously in a different season, the snow is melted, and you have a very abundant waterfall coming out from the rock. This is another example of a spring. And the feeding of this spring flow is the melting of the snow in the upland of this landscape. This is important in connection to climate change because we are observing in Northern Apennines, we will see better in the next lesson, we are observing in Northern Apennines a lowering of the snow cover falling to the ground and of the permanence of the snow to the ground. And this is a problem for the recharge to the aquifer because less snow is infiltrating down into the ground and is contributing to the discharge of the spring. An extreme case of the importance of spring flow is the oasis. Oases are discharge of abundant quantity of water in a complete arid condition, like the Sahara, for example. And why do you see water in this arid condition? Because there is a groundwater flow system that is contributing the water to the surface. Also, if at the surface you don't have rainfall at all, there is a groundwater flow system coming from other parts of the landscape where you have some rainfall falling down and recharging the aquifer, and you have the formation of this spring. This concept is important because when we are talking about the effects of climate on groundwater flow, what is the most important process affecting groundwater due to climate change is the modification of recharge. Recharge is translated in Italian in the word ricarica, and it is the process by which the water precipitated to the ground infiltrates and arrives to the water table. What is the water table? Water table, we can translate in Italian as tavola d'acqua, is a literal translation, water table, located at a certain depth below the ground. And below this water table, all the pores, you recall the pores of the porous medium, all the pores are filled by water. And the water table is important because this is the saturated part of the subsoil. So rainfall is falling, water is infiltrating down, and it arrives to the water table. But if you have an increase of high intensity rainfall event, and this is one of the consequences of climate change, the water is falling down to the surface in a more concentrated way, in a very short time. And so a bigger quantity of the water is going to flow over the surface, going toward the sea, and a less proportion of water is infiltrating down into the ground because the soil has a limited capacity to be infiltrated by the water. And if the quantity of water arriving to the ground is too much intense in a short time, a big proportion of water is flowing away and is not contributing to recharge. Concerning snow, you have the snow fall to the ground, but if you have an increase of temperature, all this snow is melting in a very rapid way. And this melting in a very rapid way produces a high quantity of water that is flowing above the surface and less water than is infiltrating down into the ground. Two ways to see how climate change could affect recharge to groundwater. And if you have less recharge to groundwater, you have less discharge. So you have less discharge of the springs and less productivity of the wells that you drill to exploit groundwater. The process of recharge of groundwater, the recharge can be different origin, from direct infiltration, from the rivers, from locations of high infiltrability in the ground, could be also incidental, also man, also the anthropic activity could induce recharge, for example, irrigation or the leaking of sewers and pipes. The drivers of recharge are effective rainfall, snow, the soil water content, and the land use, but each of them could be affected also by climate change, because climate change could induce the distribution and intensity of rainfall, the permanence of the snow to the ground, and so the proportion of recharge with respect to overland flow in the hydrogeologic budgeting of the watershed. I have a couple of slides still for today, and then we can continue the next day. You imagine here the pattern of groundwater flow here, and you see how the water table it is connected to the stream flow. So you have always to consider that groundwater is connected to surface water, are not two separate realms, are not two separate systems, but they are interconnected between each other. In this case, you see that groundwater flow is contributing to the discharge into the rivers. This is an example of unconfined aquifer and unconfined groundwater. We say in Italian aquifero libero, non confinato. And on the other hand, we have the confined or artesian aquifer, where here you have the recharge. Then you have to imagine that the groundwater flow is flowing inside the confined aquifer in a pressure condition. So if you drill a wells, the water is rising up to the surface, flowing out in like a geyser, something like that. And you can so exploit the water also at high depth into the soil. But this water is coming from a recharge area where the recharge is controlled by climate. So a modification of climate could induce also a modification of the recharge. Yeah, I think that for today it's enough, because I have so. Can I have a couple of minutes more, because I'm going to finish the slides of today, and so we are in time. This is a map of Emilia-Romagna region, where you see the main aquifers in Northern Apennines. So the lithology is more permeable for groundwater flow. Northern Apennines generally are not so permeable like Central or Southern Apennines. So the springs in Northern Apennines are not so big like the springs in Lazio, Abruzzi, Campania, or other Umbria or other region in Italy, because the permeability is lower. Take into account this conceptual scheme. It's very simple. The recharge is the process by which the water is infiltrating down to the aquifer. The groundwater is flowing from the recharge area to a discharge area, and the discharge area could be a spring, for example. If you are in a steady state conditions, the same amount is recharged, the same amount is discharged. We don't have a disequilibrium, an instability. If the recharge is going to be lowered respect to the discharge, water table is going to be lowered, and you have a lowering of the water table. Or if you exploit groundwater by wells, by pumping, by overexploitation. Also, if the recharge remains constant, you have a lowering of discharge. And so you have a lowering of the water contributing to the ecosystems and rivers and lakes. Each effect you have in the groundwater has a different output on the surface water because groundwater and surface water are interconnected between each other. Here is another example. A stream could be a factor of recharging groundwater, like here, or at the same time, a stream could be recharged by groundwater through the bottom of the stream network. So take into account the interconnection between groundwater and surface water. Surface water is more rapid, groundwater is more slow in motion, but the two systems are interconnected between each other. I recommend to you to see this small movie, 10 minutes more, that is showing you some good examples of springs, spectacular springs located all around Italy, from northern to southern Italy. It was produced by an international congress of hydrogeology some years ago. So in this first lesson, we have talked about the process. The following lesson, the following Monday, we are talking about the impacts of climate change and of global change, not only climate change, on in terms of hydrogeological instability. And we talk about mitigation and adaptation to these impacts. I have finished. If you have questions, I can reply to your doubts, if you have any doubts. They ask me if you have uploaded the slides on the system. Yeah.
10 minutes ago.
10 minutes ago. Okay. Okay. With the video, including the videos.
The video, it was already there from last year. I think.
Yes, but now they were more in a more huge number than the other time. So
I will need to replace the videos.
Okay.
So give me 15 more minutes. But for the slides, they are already there.
Okay. Thank you for your listening. See you the next Monday, the same time, same place.
Thank you.
Okay. Grazie ad Alberto, grazie a voi. Buona settimana.
Direi che possiamo chiudere, Serena e Giulia. Grazie.
Perfetto,
Sì,
grazie.
Sì, perfetto.
Grazie, grazie a voi.
Grazie, arrivederci.
Grazie, arrivederci.
Arrivederci.